You are shipping a cylindrical container of maximum volume. The post office limits the size of the container by insisting that the length of the cylinder L plus its girth, the circumference of this circular cross section with radius R, so the girth is represented by G, be limited to 84 inches. And we're asked here to find the length, radius, and volume of the cylinder with the largest possible volume. So here is a picture of our cylindrical container here. So we know from end point all the way to end point. So this distance here represents our length. And then we can even say that from the center point of either one of our circular ends, we can see our radius. So in the question, let's think about what we are given. And we can see here that the post office is limiting the size of the container such that the length plus the girth is limited to 84 inches. So we are given that the length of the cylindrical container plus the girth of the cylindrical container is equal to 84 inches. And we're also given here that the girth is equal to the circumference of the circular cross sections. So we know that the girth is our circumference here. So that's 2 pi r. So we can further rewrite our constraint as being the length plus 2 pi r is equal to 84 inches. And so this is our constraint equation. This is what we are restricted by. So now that we've sketched our graph and we've stated what's given, we want to identify what is it that we want. So looking at our question here, we want to find the length, radius, and volume of largest possible volume. So we want the length is equal to what? The radius is equal to what? So these are our dimensions. And then we want the volume of this cylindrical container. And we know the volume of a cylinder is pi r squared multiplied by the height. So in this case, it's multiplied by our length. So this volume equation here is going to be our objective. And just in looking at this, we can see that it has too many variables. So we want to use our constraint equation here to rewrite the volume in terms of a single variable. So from our constraint, I'm going to solve here for our length. So we have that L is equal to 84 minus 2 pi r. And we can now replace the L of our volume equation with the length from our post office's restriction. And let's give ourselves some more room. So we can now rewrite the volume so you can see that volume is equal to pi r squared multiplied by 84 minus 2 pi r. And I'm going to simplify this a little bit. I'm going to factor that common constant 2 out. This is going to be 2 pi times the radius squared multiplied by 42 minus pi times our radius. And then because we know we want to differentiate, I'll distribute r squared through to both terms. And so this becomes 2 pi multiplied by 42r squared minus pi multiplied by the radius cubed. And so we're now ready to go about finding the critical values. So we want to find the critical points. And we recall that to do that, we need to set the volume, the derivative of volume, equal to 0 and solve for r in this case. So differentiating, I have the derivative of volume is equal to 2 pi multiplied by 84r minus 3 pi r squared. And we can simplify it by pulling out a greatest common factor of 3r. So this leaves us with 6 pi times the radius multiplied by 28 minus pi r. And so we're now ready to set this equal to 0. So we have 6 pi times the radius multiplied by 28 minus pi times our radius is equal to 0. And I'm just going to go right ahead and remove our constants here. We can divide both sides of the equation by 6 pi. So those cancel each other out, and we are left now with r multiplied by 28 minus pi r is equal to 0. And applying the zero factor property, we have our two cases. R is equal to 0. And then we have 28 minus pi r is equal to 0, which we can simplify to the radius being equal to 28 divided by pi. So we have two possible solutions here. However, looking at this, we can disregard our first one. We cannot have 0 dimensions. So we have determined, and we should add units here, we have determined that the radius that maximizes the volume is 28 by pi inches. And so we can now use this to find the length. Remember, that was our constraint equation. So we can keep in mind that the length was defined as 84 minus 2 pi r. From our post office restriction, so substituting our radius value into r, we have that the length is equal to 84 minus 2 pi multiplied by 28 divided by pi. And we can simplify. Our pi's cancel each other out, and we have 84 minus 56 for a beautiful final answer of 28. So we can say, therefore, the maximizing length is 28 inches. So we have the dimensions that yield a maximum volume, and we'll use them now to find the max volume. So that the volume is pi r squared times the length. And plugging in what we just found, we have pi multiplied by 28 all over pi squared multiplied by 28. Oh, and shame on me, don't forget your inches. So this should be 28 divided by pi inches squared multiplied by 28 inches. And simplifying, we have pi multiplied by 28 squared all over pi squared, and this is inches squared, multiplied by 28 inches. So we can simplify. One of those pi's cancels in our denominator, and we're left with 28 cubed all over pi, and this is inches cubed. A little bit more room. So we can say, therefore, the volume, so leaving it in its exponential form, we have 28 cubed by pi inches cubed, which is equal to 21,952 all over pi inches cubed. And this is our beautiful final answer here for the maximum volume.